Hello and welcome dear students. In this video, we will discuss various types of adsorption isotherms. We know that adsorption is generally studied by plotting the amount of substance adsorbed, that is referred to as adsorbate, on the surface of unit mass of the adsorbent against pressure at various constant temperatures, or it can be also studied against temperature at various constant pressures. That is, the curves, adsorption curves obtained at different temperatures are termed as adsorption isotherm. That is, in the case of adsorption isotherm, the temperature will be kept constant and pressure is varied. This is a typical adsorption isotherm. Here, three adsorption isotherms are shown, namely one at 273 Kelvin and other at 244 Kelvin and the third one at 195 Kelvin. Based on the curve obtained for the adsorption, there are 5 major types of adsorption isotherms, namely type 1, type 2, type 3, type 4 and type 5. We will see each of them in detail. This is the curve obtained for type 1 adsorption isotherm. Here, the curve approaches a plateau. That is, you can see that as the temperature increases, the rate of adsorption also increases, and finally a plateau is reached, which means that there is a saturation of the surface of adsorbent. Here a saturation limit is reached, which again gives the idea that there is no multi-layer adsorption and there is only a monolayer adsorption, and which is many times chemisorption. This may be visualized as follows. Suppose this is the surface of an adsorbent and the adsorbent molecules will be adsorbed on the surface of this adsorbent like this. These are adsorbate molecules, and once the monolayer is complete, there is no further adsorption. That is, saturation limit is reached. This is the case that we see by the plateau of the curve. This type of adsorption is generally observed in the cases of gases on microporous solids. Microporous solids means they are the adsorbents whose pore size are less than 2 nanometer. Example for type 1 adsorption includes adsorption of nitrogen or hydrogen on charcoal at minus 180 degrees Celsius, and also the adsorption of organic vapors on zeolites and other microporous solids and molecular sieves. This is the curve obtained for type 2 adsorption. Here we can see that there is no saturation limit. That is, the curve tends to infinity, which indicates that an indefinite multilayer formation. Here there is no saturation or completion after the monolayer formation. The graph is a sigmoid function here. The first point of inflection shows the completion of the monolayer formation. This is just like the type 1. That is, up to this point, it is like type 1. This is a point of inflection A. So after A, it shows the saturation limit. That is, the case may be represented like this. Suppose if this is the surface of the adsorbent, a monolayer is formed first like this, and this is shown by the point of inflection. The point of inflection shows the completion of the monolayer formation, and after that there is a tendency where the curve extends to the to infinity. That indicates the formation of multi-layer over the first layer. This is the case. So after the formation of the monolayer, the multi-layer formation takes place in the case of type 2 adsorption isotherm. Example of type 2 adsorption includes the adsorption of nitrogen on iron or platinum at minus 195 degrees Celsius, adsorption of nitrogen on charcoal at minus 180 degrees Celsius is also an example. Adsorption of water vapor on carbon black at 30 degrees is also an example of type 2 adsorption. Now we will move on to type 3 adsorption. The curve obtained in the case of type 3 adsorption is shown here. That is a type 3 adsorption isotherm. The curve is a hyperbolic graph. The curve shows no tendency of saturation limit. That is, the curve keeps on increasing to infinity. This indicates a direct multi-layer formation. There is a second and subsequent layer formation begins before the completion of the first layer. This is unlike the type 2 adsorption isotherm. In the case of a type 2 adsorption isotherm, the multi-layer formation took place only after the completion of the first layer. However, in the case of type 3 adsorption, the case may be represented like this. This is the surface of the adsorbent. Here, the adsorption, the multi-layer adsorption takes place before the completion of the monolayer. That is, we can say that the adsorbate interaction is much more than that of the adsorbate interaction. That is, to put it in another way, we can say that heat of adsorption is less when compared with heat of liquefaction of the adsorbate. Example for the type 3 adsorption includes the absorption of bromine on silica at 80 degrees and adsorption of water on activated charcoal and hydrophobic CLH. They are the examples of type 3 adsorption. Next, we will see the type 4 adsorption isotherm. This is the type 4 adsorption isotherm. The curve obtained is shown in the figure. On comparing with the type 2 adsorption isotherm, we can easily find that this type 4 adsorption isotherm is a mere extension or variation of type 2 adsorption isotherm. That is, up to this point, it is like the type 2 adsorption isotherm. After that, a plateau is reached. So this indicates that there is a more interaction of the adsorbent and the adsorbate. So since the interaction between the adsorbent and absorbate is more, the heat of monolayer formation will be higher. That is, first of all, a monolayer will be formed, and here there is another peculiarity is that there is the adsorbent is porous material. Many times it will be porous. In the case of type 4, the adsorbent is porous and the adsorption monolayer is formed within the pores. The monolayer formation takes place like this, and as the pressure increases, we can see that the condensation takes place within the pores. This is the case. As the pressure increases, the condensation takes place within the capillary or the pores of the adsorbent. Example includes the adsorption of benzene on silica, and another example is adsorption of water vapor from humid air on hydrophilic CLH. These are the examples of type 4 adsorption. Now we will see the type 5 adsorption isotherm. The curve obtained is shown in the figure. Here the curve is an S-shaped curve, and on comparison with the type 3 adsorption isotherm, we can see that this is an extension or variation of type 3 adsorption isotherm. That is, up to this point, it is like the type 3 adsorption isotherm. After that, there is a plateau formation. That is, here the subsequent layer gets saturated. That saturation limit is shown by the plateau of the curve. Here there is a direct multilayer formation. Unlike the type 4, here there is a direct multilayer formation within the capillary or within the pores of the adsorbent. So here also the adsorbent is porous material. So type 4 and type 5 adsorption, they are porous adsorption. That is, the adsorbent consists of pores or capillaries, and the multilayer formation, direct multilayer formation, takes place within the pores itself, like this. And then filling takes place, and therefore a saturation limit is formed. Therefore, here there is a direct multilayer formation, but the formation takes place within the capillary or within the pores of the adsorbent. This phenomenon is referred to as capillary condensation. It is a multilayer formation, direct multilayer formation within the pores of the adsorbent are referred to as capillary condensation. Examples of type 5 adsorption includes adsorption of water vapor on activated charcoal at 100 degrees and adsorption of water on carbon molecular sieves. Next, we will see the use of adsorption isotherms. Adsorption isotherms are generally used to select the adsorbent as well as the adsorption process as a unit operation for the adsorptive separation of gases. That is the first use of adsorption. And the second is that if the adsorption isotherm is type 1, 2 or 4, then that adsorption technique can be used to separate the adsorbate from the carrier gas effectively. Effectively meaning by looking at the adsorption isotherm, we can decide whether the separation technique is cost effective or not. If the adsorption isotherm is say type 3 or 5, then the adsorption technique will not be economical for the separation process. Though the adsorption isotherms are indicative of the efficiency of an adsorbent for a particular adsorbate, many times they do not give the data of the contact time or the amount of adsorbent required for the removal of the required amount of adsorbate. I hope the points are very clear to you. Thank you.